It's review time. We're going to review Unit 3 and Unit 4. All right, let's go. First topic is atoms and molecules in a chemical reaction. You should know the name of this right here. And you should know the name of this one over here. Okay, these are called the reactants. That's reactants, and these are called the products. In a chemical reaction, the plus sign means that the two elements or molecules are reacting together, and then the arrow means produces, and then on the right side of the arrow you have the products. In atoms and molecules in chemical reactions, you need to know what these little subscript numbers mean. These subscript numbers tell you how many of each element are within the molecule. So for example, right here we have two nitrogen atoms. Okay, and this is one nitrogen molecule. How do I know it's one nitrogen molecule? Well, because there's not a number one written right in front, because you never need to write a number one because it's redundant because you already wrote the N. So what that tells us here is that there's going to be two hydrogen atoms, but there are three hydrogen molecules. Okay, so that's a total of six hydrogen atoms. Okay, and you'll need to know those things for this review. Oh yeah, I forgot to say. So this number in front is called the coefficient number. That tells you how many molecules there are when the coefficient number is attached to a molecule or an element. And then once again, the small number is called the subscript, and you have the reactants and the products. Okay, for this practice problem, you should identify the reactants and the products and let me know how many of each element there are, and let me know how many of each molecule there are in the chemical reaction. Whoops, it's actually not balanced, so I need to actually put a coefficient of 2 here and a coefficient of 2 here, so we're balanced. Okay, go ahead and do that, and I'll put the answer up in just a moment. 5, 4, 3, 2, 1. Okay, here's the answers. These two molecules of water are the reactants, and these hydrogen and oxygen molecules are the products because of their location in the chemical reaction. Right here we have two molecules of water, which have a total of 4 hydrogen atoms and 2 oxygen atoms. And then on the product side, we have a total of 2 hydrogen molecules and 1 oxygen molecule. And the total product atoms are going to be the same as the total reactant atoms in a balanced chemical reaction. And that's because of the law of conservation. So if you added up all the hydrogens on the product, all the hydrogen atoms on the product side and the oxygen atoms on the product side, they will equal the same amount of hydrogen atoms and oxygen atoms on the reactant side. That's a law of conservation because matter cannot be created or destroyed. It can only be rearranged into different substances. So that means the number of atoms on the reactant side and the product side will stay exactly the same. Next topic is types of elements and molecules. All right, there you go. The types of elements. First, the types of elements are the metals, the metalloids, and the nonmetals. So I believe this periodic table is in the important links to resources, and you should be able to memorize where the metals are, the metalloids, and the nonmetals just by looking at the periodic table, even if it's not color-coded. So even if it's like a periodic table like this, you should have the basic idea that the metals are on the left side, the nonmetals are up above on the right side, with the exception of hydrogen over here. Funny little rule to remember it is that people are made out of nonmetals, and we keep the guns in the basement, and guns are made out of metal. And so these are like little stair steps that go down to the basement, and these are metals. It's just a funny way to remember where the metals, metalloids, and nonmetals are. Okay, so the types of molecules you kind of depend on your knowledge of where the types of elements are. So the types of molecules are, the first one we ever learned was called ionic, And an ionic compound is when you have a metal reacting with a non-metal. Okay, and what ends up happening is the electron from the metal is transferred over to the non-metal. So that's what ends up happening in an ionic compound. Ionic compounds, an example would be like table salt, sodium chloride. Sodium would be the metal, and chlorine would be the nonmetal. When you put them together, you call it sodium chloride. Sodium chloride. Okay, the next type of molecule is one that we've been learning called the covalent molecule. And it's right there in the name, co for like cooperation, and valent referring to valence electrons. So what they're doing is they're sharing their valence electrons. They're cooperating with their valence electrons. And a covalent molecule is when a nonmetal reacts with another nonmetal. Okay, and what ends up happening is the electrons from each nonmetal, the valence electrons from each nonmetal, they end up sharing with each other. So they're sharing, they're going both ways. They're not completely transferring like the ionic electrons are, but they're sharing like this. They're sharing their valence electrons. An example of a covalent molecule is water. All right, the next type of molecule that you should know is the alloy type molecule, or you can call it metallic type molecule. An alloy type molecule, pretty simple, is between a metal and another metal. So alloys would be like brass or steel. They're made up of different types of metals, yeah. So what's happening with the electrons is there's a sea of electrons, meaning that the electrons can move around freely from nucleus to nucleus in a sample of alloy metal. They can move around freely. So the electrons can move very freely. Maybe that's a reason why alloys are great conductors of electricity. Is because they have a sea of electrons. Okay, an example of an alloy I said earlier was like steel or brass. All right, those are the types of elements and molecules that you should know, and the behavior of the electron specifically with ionic and covalent. You should know. All right, students, here's your little review questions. What type of element are each of these? Go ahead and pause the video if you need to, but I'm going to put the answers up right now. So hydrogen is going to be a non-metal type element. Oxygen is going to be a, pause the video if you haven't already to try and get these, non-metal type element. Sodium is going to be a metal type element. Silicon is going to be a metalloid type element. All right, here's your questions. What type of molecule are each of these? Go ahead and pause the video and try and answer before I give you the answers, and I'm going to give you the answers right now. Okay, so the type of molecule C3H8. If I look at this periodic table, I can see that C carbon is a nonmetal and H carbon is also a nonmetal, meaning that this is a covalent type molecule. And the electrons are sharing. You would draw like a Lewis dot structure of that, etc. Okay, let's look at next one. Carbon dioxide, CO2. Carbon is a nonmetal. Oxygen is a nonmetal. So this is also a covalent type molecule. All right, next one is aluminum nitride. This is the correct formula for aluminum nitride. And what type of molecule is this? Well, aluminum would be the metal. Nitride, nitrogen would be the nonmetal. So this is going to be an ionic type molecule. And the next one, we have aluminum, Al2O3. That's aluminum oxide. Just because there's 2s and 3s doesn't mean the type of molecule changes. It just, the little 2s and 3s let us know how many of each atom there are in this one molecule of aluminum oxide. So since there's a metal and a nonmetal, this is an ionic compound as well. And what about Fe? What does Fe stand for? You're right, it stands for iron. So this is a... No, it's not an alloy. I tricked you. I'm sorry. An alloy is when there's two metals bonding to each other, and actually molecule means when there's at least two elements there present. So Fe for iron is a metal element. This is an element, not a molecule. Sorry, I tricked you. Not sorry. Next topic is ionic compounds in chemical reactions. All right, here's the topic, ionic compounds in chemical reactions. So if we were going to write the ionic compound in a chemical reaction for table salt, well, we first are going to be using the individual elements as the reactants and then the molecule as the product. So we have sodium reacting with chlorine, and that's going to produce sodium chloride. Okay, that's an easy one. That's an easy example of what to do. Because the charges on sodium and chlorine balance, you only need one of each, and you only need one of each here. But what if we changed it to, let's say, magnesium chloride? Let's make a chemical reaction out of magnesium chloride. Okay. Well, magnesium chloride is, you start the same. You write the element symbols, and they're reacting with each other. Magnesium reacting with chlorine gives magnesium chloride. But here's the trick. This is not the correct formula for magnesium chloride. The correct formula for magnesium chloride needs a subscript of 2 right here because the charges balance that way. Remember, with magnesium having 2 valence electrons that it gives away, and chlorine has 7 valence. Each chlorine has 7 valence electrons, so it takes each chlorine takes 1 valence electron from the magnesium, and that's how the charges are balanced. Maybe if you need a review, this is what I'm talking about. There you go. Okay, so since there's a little 2 right here, you have to put a 2 in the front over here so that the chemical equation is balanced. So this lets us know that there are 1 magnesium atom reacting with 2 chlorine atoms, and it produces the correct formula for magnesium chloride. All right, and that is how to write ionic compounds in chemical reactions. Okay, here's your test. You could try and write the ionic compound in a chemical reaction for the substance aluminium oxide. That's right, I said it, aluminium oxide. Oh my goodness, I spelled that wrong. That's embarrassing. Too many I's. Ha, life, you know? Okay. I think the British people say aluminium. Anyway, so what you should be doing first is separating them into their elements. The symbol for aluminum is Al. You can pause and work by yourself and see if you got the answer right later if you want. Reacting with oxygen, and it produces aluminum oxide. Now, if you finished right here, you're like, oh, I'm done. This is great. Well, you got the answer wrong. So you need to get the correct. You need to get the correct formula for aluminum oxide. Correct formula for aluminum oxide looks like this. Aluminum has a charge of +3. Oxygen has a charge of -2. So oxygen needs to invite one more friend. And now the oxygens are winning. Look, see? -4 versus +3. Oxygens are winning. Okay, now over here, aluminum's going to be like, okay, I don't want the oxygens to win, so I'm going to invite another friend over. Now it's +6 against -4, so the aluminums are winning. So the oxygen has to invite one more friend over, and now it's +6 versus -6, and that's a balanced formula. So the correct formula for aluminum oxide would be Al2O3. Okay, and that's how you solve for the correct formulas. Now, when you balance the chemical equation, you need to make sure that there's the same number of atoms of each element on the reactant side as the product side. So we have 2 atoms of aluminum reacting with 3 separate oxygen atoms to produce 1 molecule of aluminum oxide. So yeah, hope that makes sense. Next topic is covalent molecules and drawing Lewis structures for them. All right, so this is a big review about knowing about covalent molecules and Lewis structures. So what happens to the electrons when covalent molecules are formed? Well, the electrons, the valence electrons are shared. That's why they're called covalent molecules, cooperating with the valence electrons. Okay, and they're made out of non-metals. So when we draw a Lewis structure for, say, hydrogen, for example, we know that hydrogen is in the first row, so it gets 1 dot. And that's the Lewis structure for hydrogen, right there, boom. Now, if we have another element like oxygen, we need to find oxygen, and we see that it's on the second row, and we count over from the second row to oxygen and stop at oxygen, and that's how many dots it gets. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. And that would be the Lewis structure for oxygen. Now, what if I ask you to draw the Lewis structure for a molecule like H2O? Well, we know that there's 2 hydrogens. So here's 2 hydrogens, and they have the dot. And we have 1 oxygen right here. And we know that oxygen has 6, like we just said. Well, when the hydrogens and the oxygens are sharing their valence electrons so that each element could achieve the octet rule. Remember, hydrogen only needs 2. The rest of the elements on the periodic table need 8. So there's hydrogen with its 2 valence electrons that it's sharing. And here's oxygen with its total of 8 valence electrons that it's sharing. In the end, you draw the shared electrons as lines. So it ends up looking like this. All right, and that's the water molecule. The Lewis structures and the covalent molecules for the water molecule. All right, students, sometimes covalent molecules and Lewis structures can be more complex. So you're going to want to follow these 4 rules for drawing more complex Lewis structures. And remember, there are exceptions, and here are the exceptions right here. P for phosphorus can hold 8 or 10 valence electrons. Sulfur and bromine can hold 8, 10, or 12. And boron, B for boron, can hold 6 or 8 valence electrons. So these are elements to keep in mind that break the octet rule. So there are some elements that break the octet rule, and those are them right there. Okay, here's an example. Okay, so you can see that sulfur in the middle has 2, 4, 6, 8, has 10 valence electrons surrounding it. So that would be breaking the octet rule, but sulfur is allowed to do that. And you can see bromine right here also has 2, 4, 6, 8, 10 electrons surrounding it. That's also breaking the octet rule, but that's okay because bromine is one of those exceptions. There could be Lewis structures for polyatomic ions. Okay, so for drawing Lewis structures for polyatomic ions, you'll notice that the polyatomic ion has a charge right there. That charge refers to the additional electrons that you're going to have to draw. So, what's up, Walker?
And I got green in my cup.
Oh, that's a good juice.
And I'm going to find Mama.
Okay, good luck finding Mama.
Bye, Dad. Bye, Dad.
Bye. All right, so here's this little -2 right here, and that means that you're adding 2 electrons. It's a -2 because electrons are negatively charged, and these are negative. It's a -2 because you're adding 2 electrons. So when you're drawing the Lewis structure, you just have to account for 2 extra electrons. And here's some common polyatomic ions and their Lewis structures right here for you. Not down here. Mostly like this up here. Okay, so I think I just realized you couldn't see what I was showing you, but I was showing you this right here, and I believe you can see it now. This is the little -2 I was talking about, and this is the little -2 I was talking about for a different type of polyatomic Lewis structure. Whenever you have a little -2, that's how many extra electrons you have to add to the Lewis structure. Electrons are negatively charged, so when you have a -2 charge, that means you have 2 extra electrons. Okay, hopefully that makes sense now. Let's do an example. All right, let's do the Lewis structure for NO3 minus. There it is, NO3 minus, that's -1. That's referring to -1. Sometimes you'll just see it as a minus, sometimes you'll see it as -1. They both mean the same exact thing. So how you do these more complex Lewis structures for polyatomic ions is you add up the number of valence electrons. Nitrogen brings in 5 valence electrons. Oxygen brings in 6 valence electrons. There's only 1 nitrogen, and there are 3 oxygens for a total of 5 plus 18, which is 23. And that's an odd number, but we have this -1 right here. This -1 means there's an extra valence electron, so we need to add 1 for a total of 24 valence electrons. That's our magic number for our Lewis dot structure. We can't go over, we can't go under. So we have our nitrogen will be in the middle and oxygens will be on the outside. Usually that first element is in the middle, usually, with the exception of like water and a few other molecules. And oxygens are right here on the outside. And then I say the next step is to just automatically draw single bonds to show that all of the atoms are connected within one molecule of the NO3. And each bond represents 2 shared electrons. So I just drew a total of 1, 2, 3, 4, 5, 6 valence electrons. So let's subtract 6. I have 18 more to draw. Let's draw them all over the place. Let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Wonderful. It looks great. This would be accepted as a correct answer. Oh, wait. No, this is not the right answer. I apologize. Can you identify the problem? I just identified it really quick and I forgot that it was a problem. The nitrogen in the middle is not obeying the octet rule. The nitrogen in the middle only has 6 valence electrons. That's a problem. So what we got to do is we can't just add other electrons because we already used up all of our electrons. So what we got to do is make a double bond. So you could pick any one of the oxygens. Pick any one of them. You'll get the right answer. Take off 2. Take off 2 of those unbonded electrons and make them bonded. And now the nitrogen in the middle has a total of 8 valence electrons surrounding it. And that's the correct Lewis structure for NO3 -1. Next topic is organic molecules. Yeah. That was awkward. Okay, so organic molecules are a special class of molecules that are the building blocks of life. So that's carbon and hydrogen and various other ones, various elements. Okay, but it's mostly carbon and hydrogen. And there's so much carbon and hydrogen. That's why we started deleting the carbon and hydrogen and making it look like lines and sticks. So, for example, the stick structure for C3H8, we'll say, all the carbons turn into dots, and you ignore all the hydrogens that are connected to carbons. So this molecule would end up looking like this. There's 1 carbon, there's 2 carbons, there's 3 carbons, and you connect them, showing that they're bonded with single bonds like that. And that would be the stick structure. This is the answer. This is the stick structure for this molecule right here. And that is the gist of organic molecules. Okay, here would be an example for you to do. Try and draw the stick structure for this molecule right here. You could pause the video and see if you get the answer correct later. So here it is. Looks like we have 2 sections, the CH3 and the CN. So that's 2 carbons. So here's a dot for the first carbon. And here's another dot for the second carbon. Okay, and then it looks like we have a nitrogen. Okay, well, we know that since there's 3 hydrogens, that this must be a single bond because the carbon can only have 8 valence electrons, right? So the 3 hydrogens supply a valence electron, and the carbon brings its own valence electron. So there's a single bond here. And then what we need to know about this one is that there is going to be a triple bond here because this carbon also has to be obeying the octet rule. Okay, a triple bond to the nitrogen. And that could be the stick structure. All right, the last bit of review is for the word isomers. And we just had a video on that right before break. So I'm going to refer you to that isomers video to learn that last bit. So that was your Unit 3, Unit 4 review. Test questions could be exactly like this review, or they could be a little bit different. But you should expect test questions like this review and like the ones on the worksheet that I've been giving you. All right, everybody, good luck and Happy New Year.